I follow up on my video presentation titled Diffusion in Gaseous Mixtures, wherein I had analyzed the Duncan and Tor experiments that were conducted in a two-bulb diffusion apparatus. To quickly recap, we have two bulbs connected by a narrow capillary tube. In bulb A, we have a binary mixture of nitrogen and CO2. In bulb B, we have a binary mixture of hydrogen and nitrogen. There is no hydrogen in bulb A, there is no CO2 in bulb B. At time t equal to 0, the valve connecting the two bulbs is opened, and equilibration is allowed to take place. The compositions in the two bulbs are monitored as a function of time, and the experimental data reported by Duncan and Tor in their classic 1962 paper are shown in this diagram here. Let's focus first on CO2 equilibration. The bulb A composition decreases because the CO2 mole fraction in bulb A at the start is 0.5. There is no CO2 here. So CO2 will equilibrate to a value of 0.25 in both bulbs. This is bulb B, will increase and will also reach a mole fraction of 0.25. The same is true for hydrogen. There is no hydrogen in bulb A, and bulb B has a mole fraction initially of 0.5. So the hydrogen will diffuse from bulb B to bulb A, and the equilibration process is faster than for CO2, and both bulb A and B equilibrate to a mole fraction of 0.25, which is the average of bulb A and bulb B compositions initially. Now, so far so good. Both the equilibrations of CO2 and hydrogen follow expected transient paths, where we can note an exponential approach to equilibrium. Not so with nitrogen. The compositions of nitrogen in both bulbs A and B are the same initially, equal to 0.5. And one would, or one should expect the nitrogen not to diffuse, but it does diffuse. And we note that the bulb A composition decreases, reaches a minimum, and then increases and equilibrates finally to a mole fraction of 0.5. The bulb B composition doesn't remain constant. It increases, reaches a plateau value, and then decreases. During a time period between 0 and 6 hours, we have uphill diffusion of nitrogen in the system. And the description of uphill diffusion and transient equilibration is well described by the Maxwell-Stefan diffusion, as I discussed in great detail in my chemical engineering science paper 2019, wherein the analysis of the Duncan-Tor experiments is carried out using the Maxwell-Stefan diffusion formulation, and the continuous lines here are for the solutions of the partial differential equations incorporating the Maxwell-Stefan diffusion equations, and the dashed lines are the corresponding solutions for the bulb B equilibration. Let's plot these composition profiles in composition space. I plot the experimental data for the transient equilibration in ternary composition space. This is the equilibration trajectory followed by the compositions in bulb A. This is the equilibration trajectory followed by the compositions in bulb B. We note that the equilibration trajectories followed in either bulb is not linear, but is curvilinear or serpentine in nature. And if the fluxes are assumed to be proportional to the gradients in the composition mole fractions, we should expect a monotonous equilibration trajectory shown by the dashed lines. The solution of the Maxwell-Stefan diffusion formulation is shown by the continuous lines, red in bulb A, green for bulb B. So the Maxwell-Stefan diffusion equations are able to describe quantitatively the serpentine equilibration trajectories that is followed in the experimental data. Indeed, serpentine equilibration trajectory is a signature of uphill diffusion, and in today's presentation I asked the question, why is it serpentine in character? What makes this trajectory change direction and follow a curvilinear path rather than a straight line path? The Maxwell-Stefan formulation for diffusion in the ternary gas mixture consisting of hydrogen species 1, nitrogen species 2, CO2 species 3 can be shoehorned into the form of the generalized Fick's law, in which we have a column matrix of diffusion fluxes J1 and J2 for species 1 and 2. These are related to the gradients in the mole fractions of components 1 and 2. This is a square matrix of Fick diffusivities. Vm is the molar volume of the mixture. The matrix of Fick diffusivities can be determined from the Maxwell-Stefan diffusivities for the three binary pairs 1, 2, 1, 3 and 2, 3. For hydrogen, nitrogen, CO2, the values of the three binary pair diffusivities determined from the kinetic gas theory are shown here. We note that the lowest value is for nitrogen CO2, which is 1.68 10⁻⁵ square meters per second, whereas the other two binary pair diffusivities are significantly larger because species 1 is hydrogen, which has the highest mobility. Evaluated at the final equilibrated composition, the values of the Fick diffusivity matrix is shown here. We note particularly that the off-diagonal elements D21 has a large negative value. The magnitude of this coefficient D21 is larger than the diagonal element D22, and the large negative value D21 with respect to D22 rationalizes the uphill diffusion that nitrogen experiences in the two bulb diffusion experiments reported by Duncan and Tour. We proceed further by determining the eigenvalues of this Fick diffusivity matrix. We have two eigenvalues. The first one is the larger one, 7.76, 10 minus 5, and the second one is the smaller one, 2.08, 10 minus 5 square meters per second. Corresponding to these eigenvalues, we have the eigenvectors. These are column matrices shown here. The first eigenvector is the fast eigenvector that corresponds to the larger eigenvalue. The second is the slow eigenvector that corresponds to the eigenvalue lambda 2, which is the lower of the two eigenvalues. The matrix algebra is described in detail in the textbook published in 1993 by John Wiley, and the calculation procedures are described in my Chem Science paper 2019. Watch also my video presentation, Diffusion in Gaseous Mixtures, on my YouTube channel. The next step is to plot these eigenvectors in ternary composition space and to see how these eigenvectors dictate the equilibration trajectories followed in the experiments of Duncan and Tour. The straight lines marked red are the fast eigenvectors. This is for bulb A, this is for bulb B, and the straight line marked blue is the slow eigenvector, identical for both bulbs. This is the equilibration trajectory followed in bulb A. This is the equilibration trajectory followed in bulb B. What we note is that during the initial stages of the transient equilibration process, the equilibration trajectory lies close to the fast eigenvector for both bulb A and for both bulb B and for bulb B. Towards the later stages, the equilibration process, the trajectory is indeed governed by the slow eigenvector. So the equilibration trajectory starts off being dictated by the trajectory dictated by the fast eigenvector, switches allegiance to the slow eigenvector as the equilibrium is approached. The same is true for bulb B. So the eigenvectors, respectively the fast eigenvector and the slow eigenvector, provide the rationale for the curvilinear trajectory because they provide the bounding boxes within which the equilibration trajectory ought to lie. If the Fick diffusivity matrix were to have 0 off-diagonal elements, then the eigenvalues would coincide and both fast and slow eigenvectors would collapse to give a straight line which would connect the initial compositions in bulb A and bulb B, and we would have an uncoupled diffusion path. The off-diagonal elements of the Fick diffusivity matrix cause the eigenvalues to be different. One eigenvalue is large, the other eigenvalue is small, and we have a fast eigenvector and a slow eigenvector, which have different directional paths, and the combination of these leads to a curvilinear equilibration trajectory. In my video presentation, Diffusion and Liquid Mixtures, I had described the equilibration trajectories followed in the two partially miscible phases that are contacted with each other in a Lewis stirred cell, shown here. We have here a mixture of acetone and water, and here we have a mixture of glycerol and water. When brought into contact, these two compositions would yield a mixture composition that lies in the two-phase region, and each of the two phases would equilibrate from the initial composition to the composition at either ends of the tie line. What has been observed experimentally is that the equilibration trajectories follow a curvilinear path to equilibrium in both acetone-rich phase and the glycerol-rich phase. Let's have a closer look at the equilibration trajectory in this part of the phase diagram, which is the glycerol-rich composition. And I plot that separately in this inset. This is the experimental data shown by the red circles, and the experimental data are described by a matrix of Fick diffusivities that have significant off-diagonal elements. I can determine the two eigenvalues and determine the fast eigenvector, shown by the red line, and the slow eigenvector, indicated by the blue line. The equilibration trajectory initially follows in the direction dictated by the fast eigenvector. And as equilibrium is approached, it bends its equilibration path such that it follows the trajectory dictated by the slow eigenvector. So these two straight lines, blue and red, set the bounds for the within which the transient equilibration trajectories must lie. In other words, the equilibration path relaxes first along the fast eigenvector, and as equilibrium is approached, the equilibration path is dictated largely by the slow eigenvector.